All right, today we're going to decode something we take for granted every single day, the very fabric of our reality, the three-dimensional space that's all around us.
Think about it. We move around, we build things, our entire lives exist in 3 dimensions. But how do we actually speak its language? I mean, how do you translate that gut feeling of space into a language that lets you describe a chair just as easily as the orbit of a planet?
Well, the secret is actually kind of simple. It all boils down to just 3 numbers: length, width, and height. You've probably heard of them as x, y, and z. And with just those 3 little coordinates, we can pinpoint the exact location of anything in space. So let's really dive into that. How do we make that jump from our everyday physical world to a perfect mathematical model that's built on just those 3 simple numbers? Okay, so here's the formal definition. We call it 3-dimensional space. And it's basically a mathematical system where, to find the position of any point, you just need 3 values. It's the best model we have for the world we live in. Every single point gets its own unique address, its own set of 3 coordinates. Of course, we didn't just stumble on this idea overnight. No way. Humanity's understanding of space has been evolving for thousands of years. So let's take a quick look at some of the key breakthroughs.
This journey is pretty incredible. It takes us all the way from the philosophers in ancient Greece, through the super strict geometry of Euclid, to a huge algebraic revolution in France, and then finally to the powerful language of vectors that came about in the 1800s.
And what's so fascinating is that even ancient thinkers like Aristotle had this gut feeling about it. He basically observed that any physical object is defined by its 3 dimensions, and that's it. For him, there was nothing else you needed to describe it.
But the real game changer? That was René Descartes. He came up with a system that gives every single point a unique numerical address. And just like that, bam, physical shapes could suddenly be described with algebra equations. It opened up a whole new universe of what we could analyze.
So having a map of space is great, but what about things that move through it, or push on other things? For that, we need a tool with a bit more muscle. We need vectors. So what is a vector? The easiest way to think of it is just as an arrow. An arrow in space. It tells you 2 really important things: how far, which is its length or magnitude, and which way it's pointing, which is its direction. It is the perfect tool for describing stuff like velocity or force, or even just a change in position. Now, vectors can interact in 2 really cool ways. First, you have the dot product. This one basically asks, how much are these 2 vectors lined up? Think of wind pushing a sailboat. You only care about the part of the wind that's actually pushing you in the direction you want to go. Then there's the cross product, which is totally different. It takes 2 vectors and gives you a new one that's perpendicular to both of them. This is absolutely essential for describing anything that rotates.
Yeah, check this out. This image shows it perfectly. You take vector A and vector B, and their cross product creates a brand new vector that shoots straight out at a perfect 90-degree angle to the surface they make. Honestly, this concept is the key to understanding everything, from a spinning planet to just using a wrench to turn a bolt. So, now we've got coordinates to place our points and vectors to describe all the relationships between them. With this toolkit, we can start to build the actual geometry of our world. And the range of what we can describe is just incredible. On one hand, we can precisely define a simple, perfect sphere. But on the other, we can also model something way more complex, like all the different ways that 3 flat planes can slice through each other in space. That's the power of this mathematical toolkit. Speaking of perfect shapes, let's talk about some of the most fundamental ones out there. The ancient Greeks found that there are only 5, that's right, only 5 3D shapes where every single face is the same perfect polygon. First up, we have the tetrahedron. It's built from 4 identical triangles, making it the simplest 3D solid you can possibly have. Next is probably the one we all know best, the cube, with its 6 perfect square faces. Then we've got the octahedron. A neat way to picture this one is like 2 pyramids stuck together at the base, giving it 8 triangular faces. Now things get a little more complex. Here's the dodecahedron, this really beautiful shape made out of 12 pentagons. And finally, the icosahedron. This one has a whopping 20 triangular faces, the most of any of them. And what's so amazing is, that's it. These 5 are the only ones possible. The laws of geometry just don't allow for any others. So we have our map, we have our tools, and we have our perfect shapes. But you know, the universe isn't just sitting still. To describe things like change and flow and forces,
we've got to bring in the heavy machinery, calculus.
And this is where things get really powerful. When you apply calculus to vectors, you can create something called a vector field, like what you're seeing here. These maps of little arrows let us visualize all sorts of invisible forces, like the flow of wind, the pull of gravity, or an electromagnetic field. It literally makes the unseen seen.
You know, our model for three-dimensional space works beautifully for the world we live in, but it does bring up some pretty mind-bending questions. Like, what happens if you consider spaces with 4, 5, or even more dimensions? Or what if our own space isn't perfectly flat, but is actually curved or twisted in ways we can't even perceive? In the end, it's pretty amazing that it all comes back to just 3 simple numbers: x, y, and z. From that tiny starting point, we have built a language that's powerful enough to describe not just the shape of our world, but all the dynamic forces that shape it. The universe is a really complex puzzle, for sure, but mathematics, it gives us the tools to actually start putting the pieces together.